The tool says the box was placed. The camera says it was not. This is fluid coding and AI, and today embodied intelligence becomes a state and verification test. A polished pick-and-place clip proves that a system can produce plausible actions. It does not prove the agent knows what state the task is in, whether an action has finished, or whether the job is actually complete. Those are separate problems. So the question here is brutally practical. Can an agent act, wait, observe, recover, and stop for the right reason? This is a test design, not a claimed head-to-head result. Without original traces, nobody gets to crown a winner. The comparison uses the standard and streaming Gemini Robotics ER2 preview endpoints. Both can take visual input and call functions, but they are different endpoint configurations. The standard path chains request and response interactions. The streaming path keeps a live WebSocket session and needs a heartbeat to turn fresh camera frames into explicit decisions. Streaming may feel more aware, but a socket is not consciousness. If the application never asks the model to inspect the new frame, the frame alone does not start another reasoning turn. To compare them fairly, both endpoints get the same pre-recorded warehouse episode, one timestamp checkpoint at a time. Neither gets future frames. Both receive the same task, the same tool schemas, the same action budget, and the same decision opportunities. The tools are deliberately boring: navigate, grasp, place, acknowledge, and reset. Navigate, grasp, and place are blocking physical actions. Acknowledge records the latest observed state without changing the world. Reset returns the controller to a known ready state after verified completion or an explicit timeout. Now for the part that changes the test completely. Place returns success, but the next frame shows the box balanced on the conveyor lip. Which source wins, the tool receipt or the world? A robust agent treats the response as telemetry, not ground truth. It refuses to finish, acknowledges the mismatch, and plans from the newest evidence. This is the embodied version of an API returning 200 OK while the database is still on fire. Green status lights are comforting. They are not proof. Before injecting faults, run a clean control. The agent navigates, waits for resolution, reobserves, grasps, waits again, places the object, and closes only after a fresh frame confirms the box is inside the target. This matters because permanent suspicion is not robustness. An agent that never declares completion fails too. Then delay a physical action across several checkpoints. New frames may arrive, but the prior action is still blocking. The correct behavior is to wait or acknowledge, not stack another motion command on top of an unfinished one. Next, move the blue tote after navigation but before grasp. The old plan is now stale. A plan follower reaches toward yesterday's location. A state-aware agent grounds the tote again and changes its next action. That single disturbance is useful because stale beliefs compound. If the agent misses the move, every later decision can look internally consistent while being physically wrong. The test should reward recovery from the updated frame, not loyalty to a beautifully formatted plan. Then stall the conveyor. For several checkpoints, nothing meaningful changes. The agent must not hallucinate progress, but it also cannot wait forever. The harness defines a deadline and eventually emits a timeout. Before that deadline, patience is correct. After it, the agent should reset or replan from the newest observation within a limited recovery budget. This separates controlled waiting from a frozen loop. In distributed systems terms, silence is not success, and eventually it becomes a state transition. Underneath the episode is a hidden state machine. An action moves from requested to pending to resolved or timed out. Only then does the observation update. The agent never sees those labels. It sees frames, timestamps, tool responses, and explicit timeout events. A deterministic judge sees the hidden truth. That separation is crucial. Otherwise, a persuasive explanation can be mistaken for correct control. The combined run applies the delay, moved object, false success, and stall in one episode to test whether an early mistake poisons everything that follows. Do not compress this into one robot score. Measure progress, state accuracy, blocking compliance, change recovery, false success rejection, and stall recovery separately. Then measure terminal precision and recall. Precision asks whether finished declarations were actually supported. Recall asks whether genuinely completed episodes were correctly closed instead of drifting forever. Verified episode success requires both the completed world and the correct terminal commitment. Efficiency still matters, but only after correctness. Report counts with rates, repeat across layouts and fault timings, and keep the raw traces so confident pros cannot grade itself. There is evidence that this distinction matters, but it does not answer this head-to-head. Google reports 57.4% accuracy on its 5-bin progress classification evaluation, plus 91.3% accuracy and 0.96 seconds mean absolute distance for moment finding. Those are provider-reported results on their tested suites, not scores for this 5-tool harness. Separately, the Vigil preprint evaluated 1,000 frozen episodes across 20 models and found gaps as large as 19.7 percentage points when correct stopping was required in addition to world completion. Getting there and knowing you are the limits are just as important as the design. Inert tools remove motor noise, calibration, grasp physics, collision avoidance, and real safety constraints. A pre-recorded episode gives repeatability, but one trajectory is a case study, not a universal benchmark. Vision can also be ambiguous. Glare, occlusion, low contrast, and sparse frames can hide a failure, so production systems need more than camera evidence alone. And because the endpoints differ in transport and features, any result belongs to the full endpoint configuration. It cannot prove that streaming itself caused the difference, or that either system is safe to run a warehouse. The practical standard is a closed loop: act, wait, observe, verify, recover, and stop. A robot demo proves the plumbing. This test asks whether the agent can govern the loop when the plumbing gets inconvenient. Run clean controls, isolate each fault, counterbalance the order, and finish with the combined episode. Until raw endpoint traces exist, the honest verdict is the test protocol itself. Do not trust a command because it was issued, a receipt because it was green, or a finish because it sounded confident. Trust the newest evidence and score the commitment. If this gave you a better way to test embodied AI, like the video and subscribe to Fluid Coding and AI for more practical model and developer tool breakdowns.